Find somewhere comfortable tonight, somewhere your body can be heavy and your thoughts can wander wherever they need to go. You don't need to follow any of this closely. You don't need to remember a single word. Just let the sound of the sentences arrive and let them drift past again, the way clouds move across a dark sky, present for a moment, then quietly gone. We're going to spend some time tonight with one of the oldest, most patient stories in the universe. It's the story of how certain stars live and die, how they burn for millions of years, slowly, quietly, building something inside themselves, and how, at the very end of that long life, in less time than it takes your heart to beat once, everything changes. It's a story about fire and iron and the strange behavior of matter under pressures no human being will ever experience. But it's also, in a gentle way, a story about endings and beginnings, about how nothing in the universe is truly wasted, about how the atoms in your body, in your hands, in your blood, in the bones of your chest rising and falling right now, were forged inside stars that died before our sun was born. You don't need to concentrate on any of that. It's just something to let wash over you the way water moves over stone, slow and soft and ancient. So settle in, let your shoulders go. The day is already behind you, and tonight there is nowhere to be but here, drifting slowly through one of the deepest, most beautiful stories the universe has to tell. Somewhere in the darkness between stars, a cloud of gas and dust begins, very slowly, to fall toward its own center. This is not something you would notice if you were watching. It happens over hundreds of thousands of years, patient beyond all imagining. The cloud gathers itself, grows denser, and at its heart, under the mounting weight of all that gas pressing inward from every direction, something ignites. A star is born. Most stars that are born this way are modest, quiet things. Our own sun is one of them. A gentle, medium-sized star that has been burning for about 4.5 billion years and will continue burning for roughly another 5 billion before it runs out of fuel. The sun is warm and reliable. It does not have a dramatic ending ahead of it. When its fuel is finally spent, it will swell and dim and fade, a long, slow exhale into the dark. But some stars are born much larger, born with 10 times, 20 times, even 50 or 100 times the mass of our sun packed into a single burning object. These are the giants, and their lives and their deaths are a different story altogether. It helps sometimes to try to hold the scale of it. The sun is large enough that more than 1 million Earths could fit inside it. If the sun were hollow, you could pour 1 million of our worlds into it and still have room. Now imagine something 10 times heavier than that, 20 times. The largest known stars are so vast that if one were placed where our sun sits, its outer surface would extend past the orbit of Jupiter, a planet so far from us that sunlight takes more than 40 minutes to reach it. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter itself, all of it inside the star. These are the objects we're spending time with tonight. What keeps a star like this from simply collapsing under its own enormous weight? The answer is fire, or more precisely, the outward pressure that fire creates. Deep inside every star, there is a constant process of tiny particles being pressed together under immense heat and gravity until they merge. When they merge, they release energy. And this outward push, this steady, patient pressure of nuclear fire exactly balances the inward pull of gravity pressing all that gas toward the center. A star is a tug of war. On one side, gravity, relentless and ancient, always pulling inward. On the other, the heat and pressure of nuclear fire, always pushing out. For millions of years, these two forces hold each other in perfect, unhurried balance. The giants burn fast. A star with 10 times the mass of our sun burns through its fuel. perhaps 1,000 times faster than the sun does. Where the sun will live for 10 billion years, these massive stars live for only a few million. In cosmic terms, that is brief, a bright, furious life, and then something else entirely. Throughout all those millions of years of burning, the star is quietly building something inside itself. Layer by layer, like sediment settling to the bottom of a deep, still lake, the products of all that nuclear fire are accumulating at the core. The star is, without any intention, constructing its own ending. It doesn't know this, of course. Stars don't know anything. But there is something almost moving about the image. This vast, ancient furnace, burning in the dark, slowly and patiently making the thing that will one day still it forever. For now, though, it burns on, patient, enormous, unhurried. A slow engine running in the deep quiet of space, with millions of years still ahead of it, and something heavy and inevitable growing, grain by grain, at its heart. To understand what is building inside a giant star, you have to come inside with it, past the outer layers of hot gas, past the roiling surface, down through shell after shell of burning material, all the way to the core. It's a journey through layers of heat and pressure that increase with every step inward, like diving into an ocean that never stops getting deeper and heavier. At the very beginning of a massive star's life, the fuel at its core is hydrogen, the simplest and most abundant element in the universe. Each hydrogen atom is just a single tiny particle called a proton, the smallest building block of an atomic nucleus. At the extreme temperatures and pressures of the stellar core, these protons are moving so fast, pressed so closely together, that when two of them collide, they don't simply bounce away. They stick, they merge, and in the merging, they release a small burst of energy. Think of it like two drops of water on a window pane, drifting slowly toward each other. When they finally touch, they combine into one larger drop. And in the process, something is released. In the case of water, it's just the energy of surface tension. In the case of hydrogen nuclei at the heart of a star, what's released is light and heat on a scale that is difficult to hold in the mind. This process, protons merging into larger nuclei, is called nuclear fusion. The word fusion just means joining. Tiny things joining together to make slightly larger things, releasing energy in the process. It happens billions of times per second in the core of a star, and the steady accumulation of all that released energy is what pushes outward against gravity's pull. The hydrogen burning stage is the longest. For a massive star, it lasts millions of years, but hydrogen doesn't burn forever. Gradually, the core fills with the product of all that merging, helium. Helium nuclei are made of two protons and two neutrons bound together, a slightly heavier, more compact package than the hydrogen that went in. When enough of the core has been converted to helium, hydrogen burning at the center slows and stops. But gravity never stops. With the outward pressure reduced, the core contracts a little, heats up further, and at these new, higher temperatures, something remarkable happens. 3 helium nuclei can be pressed together to form a carbon nucleus, and the process continues, releasing more. Meanwhile, the hydrogen burning doesn't disappear. It moves outward into a shell surrounding the helium burning core. The star now has layers. A core of fusing helium wrapped in a shell of fusing hydrogen, and the outer layers of the star, still mostly hydrogen, puff outward as the interior heats up, making the star swell and redden, a red supergiant, enormous and slow and ancient-looking, glowing like an ember in the dark. The helium-burning stage is shorter than the hydrogen-burning stage, much shorter, and when it ends, the same thing happens again. The core contracts, heats up further, and the carbon left behind begins to fuse into heavier elements still. Each stage is shorter than the last. Each stage happens at higher temperatures and pressures, and with each stage, another shell is added to the star's interior, a new layer of burning material wrapped around all the layers that came before. The star builds up its structure the way an onion builds up its layers, concentrically, one around the other, each one made of different material, each one burning at a different rate. Hydrogen burning takes millions of years. Helium burning takes hundreds of thousands. Carbon burning takes perhaps 1,000 years. The stages after that, neon, then oxygen, take years, then months. The star is accelerating towards something, though it has no awareness of this. The furnace at its heart is running hotter and faster with every stage, burning through its fuel more and more quickly, as though time itself is speeding up inside it. And then, finally, deep in the core, surrounded by all those burning shells, the last stage begins. Silicon, a nucleus made of 14 protons and 14 neutrons, built up through all the previous stages of burning, begins to fuse. Silicon burning is extraordinarily fast. It takes, at most, a few days, sometimes less than a day. And what silicon burning produces, at the end of its brief, furious run, is iron. The star is now an onion with a heart of iron, wrapped in shells of silicon, oxygen, neon, carbon, helium, and hydrogen, each burning at its own temperature, each slowly adding to the iron core at the center. It is a structure of extraordinary complexity, built over millions of years of patient burning. And it is almost finished. Iron is one of the most familiar elements in the world. It's in the soil beneath your feet, in the core of the earth far below that, in the nails that hold buildings together, in the bridges that carry traffic across rivers. It's in your blood. The iron in hemoglobin is what allows your red blood cells to carry oxygen through your body. You are, in a very real sense, partly made of iron. And that iron came from somewhere. It came from stars. But there is something about iron that makes it unlike any of the lighter elements that came before it. Something quiet and absolute. To understand it, you have to think about what has been happening inside the star all along. Every stage of nuclear burning, hydrogen fusing into helium, helium into carbon, carbon into neon and oxygen and silicon, every one of those stages releases energy. The merging of smaller nuclei into larger ones gives something back. There is a kind of generosity to it. The star presses its particles together, they join, and in joining they release warmth. That warmth is what the star has been living on for millions of years. But iron is different. Iron sits at a particular point in the universe's accounting, a kind of balance point, a place where the energy stored in the bonds between particles inside a nucleus is at its very lowest. It costs energy to build something larger than iron, and it costs energy to break iron apart. Iron is, in a sense, the most stable thing matter can be. It is the bottom of a very deep valley. Everything else, lighter or heavier, sits higher up the slope. What this means for the star is simple and final. When silicon fuses into iron, no energy is released. The iron just sits there, heavy, inert, accumulating. The star can no longer use its iron. It cannot fuse it further to generate heat and pressure. Iron is the end of the road, the ash that doesn't burn. And so, as silicon burning continues in the shells above, the iron core at the center simply grows, slowly, steadily, silently heavier. There is something almost meditative about this image, if you let yourself sit with it. This star has been burning for millions of years. It has fused hydrogen and helium and carbon and a dozen other things. It has built a structure of extraordinary layered complexity. And now, at the end of all that work, it is quietly filling its own heart with something it cannot use, a substance that gives nothing back. Iron has a long human story too. For thousands of years, the ability to work iron was the difference between civilizations that could arm themselves and those that could not. The Iron Age, that period when human beings first learned to smelt iron from ore and shape it into tools and weapons, transformed the ancient world. Iron plows turned harder ground than any before them. Iron swords outlasted bronze. The Roman legions marched on iron nails. The railways of the Industrial Revolution were laid on iron rails. And all of that iron, every sword, every plow, every nail, every rail, was forged originally in the hearts of stars that died before our solar system existed. The iron in your blood was scattered into space by a stellar explosion billions of years ago, drifted through the void, gathered into the cloud that became our solar system, sank into the forming Earth, cycled through rock and ocean and living things for billions of years, and eventually found its way into you. The iron in a star's core has its own quiet dignity then. It is not a failure. It is the culmination of a long, patient process of building, the heaviest thing the star's own fire could make, and it is, in the end, a kind of gift. Everything the star has built, it will eventually give away. But first, the iron core must grow heavy enough to matter, and this takes time. The core grows and grows and grows, day by day, though there are no days in the star, no sunrise or sunset, only the slow accumulation of iron settling inward. The core becomes denser, heavier, more compressed. The particles inside it are pressed ever more tightly together by the weight of all the gas above. There is a limit to how much this can continue, not a sharp line, but a threshold, a mass beyond which the iron core can no longer support itself. As it approaches that threshold, the star is balanced on the edge of something vast and irreversible. The burning shells above continue their work, unaware. Silicon fuses to iron in the shell just outside the core. The iron falls inward. The core grows heavier. And then, one quiet moment. One moment that has no drama from the outside, no visible sign, no light escaping to warn the universe. The threshold is crossed, and the iron core begins to fall. What happens next is the most violent event in the ordinary life of the universe, and it happens in a fraction of a second. The iron core, which has been growing for days, begins to collapse inward under its own weight, not slowly, not gradually. There is no warning, no gradual dimming of the fire. One moment the core is in balance, heavy, dense, but supported. The next moment, the support is gone, and the core is falling freely inward, every part of it rushing toward the center at a speed that is, within moments, a significant fraction of the speed of light. To understand why the support disappears so suddenly, you have to think about what was holding the core up in the first place. By the time the iron core reaches its critical mass, the nuclear burning that sustained earlier stages is over. What remains? The last thing standing between the core and freefall is a subtler kind of pressure. The particles inside the core, particularly the electrons, resist being squeezed too close together. Not because of any force like gravity or electromagnetism, but because of something deeper in the nature of matter itself. Particles of the same type simply refuse to occupy the same space at the same time. It's a crowding effect, a kind of quantum stubbornness, and for a while it is enough to hold the core up. But the iron core keeps growing heavier, and at a certain point the weight becomes too great even for that resistance. The electrons are overcome. The core begins to fall. And here is where things become strange. As the core collapses, it heats up, just as any gas heats up when compressed. But the temperatures reached in this collapse are almost beyond imagining. The core reaches temperatures tens of billions of times hotter than the surface of the sun. At these temperatures, the photons of light bouncing around inside the core carry so much energy that something extraordinary happens. They begin to shatter the iron nuclei. Remember that iron represents the end product of millions of years of nuclear burning. Every iron nucleus in the core was built up, piece by piece, through stage after stage of fusion. And now, in a fraction of a second, those nuclei are being torn apart again. The intense light of the collapse has enough energy to break iron back into smaller pieces, back into the helium nuclei it was once assembled from, and then further still into individual protons and neutrons. Millions of years of construction undone in less time than it takes to draw a breath. But even this is not the end of the sequence. As the core continues to collapse, the density and temperature climb higher still. Now the individual protons and the electrons that are also present in the core are being pressed together so forcefully that they merge. A proton and an electron combine to form a neutron, a neutral particle with no electrical charge. And in each of these tiny mergers, a particle is released, a neutrino. Neutrinos are among the strangest things in the universe. They are almost massless, so close to having no mass at all that for decades physicists thought they truly had none. They have no electrical charge. They interact with ordinary matter so weakly that they can pass through an entire planet as though it were not there. The Earth right now is being passed through by trillions of neutrinos every second, streaming outward from the sun, and almost none of them interact with anything. They are the closest thing the universe has to nothing that is still something. And in the collapsing core of a dying star, they are being produced in numbers that are, genuinely, beyond comprehension. In a matter of seconds, the collapsing core releases more energy in the form of neutrinos than the sun will release in its entire 10 billion year lifetime. Not more than it has released so far, more than it will ever release. All of it in a few seconds, pouring outward in a flood of almost nothing particles. The collapse is now happening on a timescale that has no human equivalent. The core, which began as a ball of iron roughly the size of Earth, collapses to a sphere perhaps 20 kilometers across, roughly the size of a city, in less than a second. Less than half a second, less perhaps than a quarter of a second. The entire interior of a star compressed to something you could drive across in minutes, in a time too short to measure without instruments. And then something stops it. When the collapsing core reaches a certain density, a density so extreme that the material inside it is as tightly packed as the nucleus of an atom, something changes. The same deep stubbornness that electrons showed earlier, now expressed by neutrons and at far greater density. The core stiffens. Almost instantaneously, it goes from collapsing to rigid. The outer layers of the star have been falling inward behind the core, chasing it down, accelerating toward the center. And now they hit this suddenly rigid surface at a substantial fraction of the speed of light. The collision is not like anything in ordinary human experience. It's more like if you can hold the image. Dropping an ocean onto a cannonball, the infalling material strikes the dense core and rebounds. A wave of pressure travels outward through the star, pushing against the still infalling layers from above. This outward moving wave is the beginning of what will eventually become a supernova explosion, but it doesn't immediately succeed in blowing the star apart. The wave runs into the dense infalling material above and stalls, losing energy, struggling to push through. For a fraction of a second, it seems as though the wave might simply die there, absorbed into the collapsing star. And this is where the neutrinos play their remarkable role. The flood of neutrinos pouring outward from the core, those almost nothing particles that ordinarily pass through everything without touching it, are so extraordinarily numerous in this moment that even their tiny probability of interacting with matter adds up. A small fraction of them, passing through the dense, infalling layers just above the stalled wave, deposit a small amount of their energy into that material. And that small amount of energy, distributed through the right region at the right moment, is apparently enough. It reinvigorates the stalled wave. The details of exactly how the neutrinos manage this are still being worked out. Astrophysicists running simulations on some of the most powerful computers in the world are still refining their understanding of the precise mechanisms. The wave stalls and revives in complex, three-dimensional patterns, the material above it churning like a boiling liquid, the neutrinos threading through it all. It is one of the most complex events in nature, and the fact that the explosion succeeds at all is, in some ways, still a subject of quiet wonder. But succeed it does, in most cases, in most stars. Now, the neutrinos themselves, they pour outward through the star and out into space, moving at nearly the speed of light, carrying with them the vast majority of the energy released in the collapse. The visible explosion, for all its brightness, carries only about 1% of the total energy. The other 99% leaves as neutrinos, invisible, nearly undetectable, streaming outward in every direction. And here is where one of the most remarkable moments in the history of astronomy enters the story. On the 23rd of February 1987, a star in a small galaxy neighboring our own, the Large Magellanic Cloud, a faint smudge visible in the southern sky, collapsed and exploded. The light from the explosion reached Earth about 3 hours after the collapse itself, having traveled roughly 160,000 light-years through space. But before the light arrived, about 3 hours before, detectors buried deep underground in Japan and the United States and Russia registered something. Each detector was a vast tank of water or other material, surrounded by sensitive instruments designed to catch the rare moment when a neutrino actually interacted with an atom. On that February morning, each detector registered a handful of interactions, a small cluster of events arriving within seconds of each other. A handful of interactions out of the incomprehensible flood of neutrinos that had passed through the Earth. Most of them went straight through the planet, through the detectors, through everything without leaving a trace. But a few, just a few, touched something, and those few touches were enough. It was the first time in history that human instruments had detected the neutrinos from a collapsing star. The first time we had felt, however faintly, the breath of something dying 160,000 light-years away. The detectors registered the neutrinos 3 hours before the light arrived because the neutrinos travel almost at the speed of light and pass through the star instantly, while the light had to fight its way outward through the dense stellar material before it could escape. That moment, those few faint signals in buried tanks of water, remains one of the most extraordinary things science has ever witnessed. A whisper from a dying star, arriving across a distance so vast that the star itself was already ancient when our ancestors first walked the Earth. The shockwave, reinvigorated by the neutrinos, travels outward through the star. It moves through the silicon shell, the oxygen shell, the neon and carbon and helium, gathering energy and material as it goes. It reaches the outer layers, still mostly hydrogen, still burning in their own quiet way, unaware of what is happening below. Unaware of what is happening below. And then it breaks through the surface. The star, which has been burning for millions of years, is torn apart in a matter of hours. The outer layers are blasted outward at speeds of tens of thousands of kilometers per second. The light released in this event, a core collapse supernova, is so intense that for days or weeks, a single dying star can outshine an entire galaxy. Hundreds of billions of stars, all their combined light outshone by one. The 1987 event we spoke of, the collapsed star in the neighboring galaxy, was visible to the naked eye from the southern hemisphere. Something that had happened 160,000 years ago, its light finally arriving, bright enough to see without a telescope. A new point of light in the sky, where there had been none before. In the expanding cloud of gas and dust thrown outward by the explosion, something interesting is happening. The extreme energies involved, the heat of the shockwave, the flood of neutrinos passing through the material, are creating conditions in which elements heavier than iron can be built. Remember that iron is the end of what ordinary stellar fusion can make. But in the violence of a supernova, there is enough energy to push matter past that barrier. Gold, silver, uranium, platinum. The heavy elements that cannot be made inside a living star are forged in the death of one, scattered outward into space with the expanding debris. The gold in a ring, the silver in a photograph, the uranium in a reactor, all of it was made in the death of a star. All of it passed through a moment of extraordinary violence before it drifted through space, gathered into a new solar system, sank into a forming planet, and eventually became something quiet and familiar. But what about the core? What was left behind when the outer layers were blasted away? In many cases, what remains is a neutron star, the dense ball of neutrons formed in the collapse, now exposed, cooling slowly in the dark. A neutron star is one of the strangest objects in the universe. It has roughly the mass of our sun, all of that packed into a sphere perhaps 20 kilometers across. If you could place a neutron star on the surface of the Earth, its gravity would crush everything around it instantly. A single teaspoon of its material would weigh as much as a mountain range. Neutron stars spin. When the original stellar core collapsed, it sped up, the same way a figure skater pulls in their arms and spins faster. Some neutron stars rotate hundreds of times per second, sweeping beams of radio waves around the sky like cosmic lighthouses. These are called pulsars, and when the first one was discovered in 1967, the signal was so regular that the astronomers who found it briefly wondered whether it might be artificial, a signal from somewhere else. They gave it the half-joking designation LGM-1 for Little Green Men. It was, of course, a spinning neutron star, but the fact that the thought occurred at all says something about how strange and precise these objects are. A neutron star is, in a sense, the last stand of matter. It is as dense as matter can be while still remaining matter in any recognizable sense. The neutrons inside it are packed together as tightly as the particles inside an atomic nucleus, which is, as far as we know, about as tightly as anything can be packed and still resist further compression. But sometimes the remnant core is too heavy even for that resistance to hold. The mass of the remnant core depends on how much of the star's material was blown away in the explosion and how much fell back inward afterward. In many supernovae, enough is blown away that what remains is a neutron star, stable, dense, spinning in the dark. But in some cases, particularly when the original star was very massive, the remnant core is heavier, too heavy. There is a point, roughly 2 or 3 times the mass of our sun, though the exact number is still a subject of careful research, beyond which even the resistance of neutrons cannot hold. The same deep stubbornness that stopped the collapse the first time, the same refusal of particles to be pressed any closer, is overcome again. And this time, there is nothing left to stop what happens next. The neutron star begins to collapse. This second collapse is not like the first. The first collapse of the iron core was halted by the neutrons. This one has no flaw. There is no denser form of stable matter waiting to catch it. The neutrons are crushed past the point where they retain any individual identity. The particles press closer and closer, and the space between them, which was already vanishingly small, shrinks further and further and further. What happens at the very end of this process is something that our understanding of physics cannot fully describe. The particles appear to be compressed toward a single point, a place of infinite density, where the ordinary concepts of distance and space and time cease to work in the ways we're familiar with. This is the singularity at the heart of a black hole, and it is, genuinely, one of the places where human knowledge quietly runs out. But before that point, something else has already happened, something visible, in a sense, from the outside. As the collapsing neutron star shrinks, the gravity at its surface grows stronger. The escape velocity, the speed you would need to travel in order to escape the gravitational pull, climbs. For the Earth, the escape velocity is about 11 kilometers per second. For a neutron star, it is already a substantial fraction of the speed of light. And as the neutron star collapses further, that escape velocity climbs toward the speed of light itself. And then it reaches it. At the moment when the escape velocity at the surface equals the speed of light, something changes in the fabric of space around the object. A boundary forms, not a physical surface, not a wall or a membrane, but a threshold in space. The point beyond which anything that crosses, any particle, any light, any signal of any kind, cannot turn around, cannot escape, cannot send any information back to the outside universe. This boundary is called the event horizon, and the object it surrounds is a black hole. The event horizon is not a place where anything dramatic happens to something crossing it. If you were falling through it, which is not something you would want to do for reasons we'll come to, you might not notice the moment of crossing. There is no wall, no flash of light, no sensation. You simply pass through a region of space that looks, to you, much like any other. It is only from the outside that the horizon has meaning. From the outside, something extraordinary happens to the appearance of an object falling toward the horizon. As it falls inward, the light it emits has to climb against an ever stronger gravitational pull to reach you. Climbing against gravity costs energy, and light that loses energy shifts toward the red end of the spectrum. It becomes redder, dimmer, stretched. An object falling toward a black hole appears from a safe distance to slow down. Its light reddens, it grows dimmer, and it never quite arrives from your perspective. It fades and reddens and stretches towards stillness, hovering at the horizon like a memory that never quite disappears. From the perspective of the falling object, though, the crossing happens in silence. In ordinary time, you fall through, and then, depending on the mass of the black hole which determines how large the horizon is, you have some time remaining before the geometry of space inside pulls everything toward the singularity. For a small black hole, this time might be fractions of a second. For a very large one, it could be hours. But there is no way back. Whatever falls in, stays in. The information about what crossed the horizon is locked away from the rest of the universe, perhaps forever. There is something almost restful about this image, if you let it settle. All that violence, the millions of years of burning, the shattering of iron, the collapse, the explosion, the second collapse, and at the end of it, this, a boundary of silence, a place where the universe keeps its secrets, perfectly still from the outside, unreachable. Pull back now. Pull back very far. Our galaxy, the Milky Way, the river of faint light you can sometimes see on a clear, dark night, contains somewhere between 200 and 400 billion stars. Most of them are small and quiet, burning steadily for billions of years, like our sun. But a fraction of them are massive enough to end their lives in the way we've been describing tonight. And our galaxy is old. It has been forming stars for more than 13 billion years. In all that time, a great many of those massive stars have already lived and died. They have burned through their hydrogen and helium and carbon and silicon, built their iron cores, collapsed, exploded, and left their remnants drifting in the dark. Astronomers estimate that there may be as many as 100 million stellar mass black holes scattered through our galaxy alone. Perhaps more. Most of them are invisible. They are not consuming nearby gas or stars, so they produce no light, no X-rays, no detectable signal of any kind. They simply drift. Orbiting the center of the galaxy as any other object orbits, following the same gravitational laws, taking the same slow, unhurried paths through the dark. If you were to pass close to one, you would feel its gravity, the same way you feel the gravity of any massive object, but you would see nothing. A region of space that looks like any other region of space, with something very heavy and very dark at its heart. There is a kind of peace in this image. 100 million objects, each one the compressed remnant of a star that burned for millions of years, now utterly still. All that fire, all that light, all that slow accumulation of iron and the violence of collapse, reduced to silence. To a quiet point of darkness, drifting between the stars. The closest known black hole of this kind is roughly 3,000 light-years from Earth. That is, in galactic terms, not very far. 3,000 light-years is like being in the same neighborhood, in a galaxy that is 100,000 light-years across. It is not doing anything interesting, not consuming material, not producing any detectable signal. It is simply there, in the dark, orbiting quietly, as it has been doing for perhaps millions of years. And then there are the questions we cannot yet answer. What truly happens inside a black hole? What is the singularity really? The mathematics that describes the formation of a black hole also produces, at the very center, a point where the equations stop working, where the numbers become infinite and the description breaks down. This is not a sign that something magical is happening. It is a sign that our description is incomplete, that the tools we currently have for understanding the universe, as powerful as they are, reach their limit here. The singularity is not an answer. It is a question mark. A place where our understanding gently runs out. What happens to the information about matter that falls into a black hole? This has been one of the deepest puzzles in physics for decades. The laws of physics as we understand them suggest that information about the state of a physical system is never truly destroyed. It can be transformed, scattered, hidden, but not erased. But a black hole seems to swallow information and lock it away forever. Whether that information is truly gone or whether it is somehow preserved in some form we don't yet understand is still an open question. It is one of the places where the two great pillars of modern physics, the theory of gravity that describes the large-scale universe and the quantum theory that describes the behavior of particles, have not yet been reconciled. These are not failures. They are frontiers, the edge of a map where the known world ends and something else begins. And there is something quietly beautiful about the fact that the universe still has edges like this, places where human understanding arrives, looks out, and rests. Now, one last image to carry with you into sleep. The star that eventually became a black hole, that vast, ancient furnace, burning for millions of years, did not disappear cleanly. When it exploded, it scattered most of itself into space. All those layers, the hydrogen, the helium, the carbon and oxygen and silicon and all the rest, blown outward into the surrounding interstellar medium. A slow, expanding cloud of gas and dust, drifting outward over millions of years, mixing with the gas already there. Eventually, some of that material gathered into new clouds. New clouds collapsed into new stars. Around some of those new stars, planets formed, and on at least one of those planets, the carbon and oxygen and nitrogen and iron in that scattered material became part of living things, became soil and water and air, and eventually, over billions of years of slow biological change, became something that could look up at the night sky and wonder where it came from. The iron in your blood was forged in a star. The carbon in your bones was made in a stellar core, scattered in an explosion, drifted through space, gathered into this solar system, and found its way through billions of years of patient transformation into you. You are, in a very literal and unhurried sense, made of the remnants of stars that died before the Earth existed. The universe has been building toward you for a very long time, and it did not do so quietly. But tonight, none of that matters. Tonight, you are here, and the universe is vast and dark and patient around you, and the black holes are drifting silently in the space between the stars, and the questions are resting at the edges of the map, and everything that needed to happen to bring you to this moment has already happened long ago in fire and silence. The day is far behind you now. Whatever it held, it's already distant. The stars are doing what they have always done, burning and collapsing and scattering themselves across the dark. Drift now, if you're ready. Keep well.